All right, my friends, let us begin on the next one, which I felt this one was appropriate for the problem that we did just before, and I think it has something that's really important for us to keep in mind as we get closer to the AP exam. Now, we consider this differential equation. Let y equal f of x be the particular solution to the differential equation with initial condition. Let the function f be defined for all real numbers. A portion of this slope field is given below. Sketch the solution curve. So we're not actually sketching the slope fields like we've done in class. We're sketching the solution curve through the point 0, 1. So I think it's important that we go through and mark at point 0, 1, which is right there. And we want to sketch a solution curve. Well, the solution curve really just us following how would the function look like. If this is your derivative function, your slope fields, how would the original resemble, right? Because you got all these slope fields. Well, it looks something like this. And you could just follow it down through, right? Boom, there it is, right? You can kind of see, right? Well, let me just backtrack. All right, we want to sketch the solution field for the function below, which is we want to try to get the best accurate at 0, 1. What is the original function? How does that original function look like, right? Well, follow the slope fields. The slope fields, if I follow this curve up here, looks something like this, right? Notice I'm just following the curve as it goes through. Here I'm following the slope fields, right? I'm following the slope fields. As I go through, I'm just following and sketching my way through. Bam. Right? And that's how I feel like the solution should look like. I'm just following the curves along the way. Bam. 1 point. We are in business, ready to roll. And we go on to the next question. I just wrote the question down below. Remember, part A was that slope field. We don't need it no more. So here it is, question number 6. Part B, write an equation for the line tangent to the graph of solution curve in part A at the point 0, 1. Use the equation to approximate f of 0.2. So write an equation for the line tangent. I mean, that to me tells me y minus y1 is equal to m x minus x1, 0, 1. Very beautiful. Y minus 1 is equal to m x minus 0. And let me change colors. So really we got y minus 1. What is our slope? Well, we're going to get the slope by plugging it in, right? So dy dx is going to be, we're plugging this in. Obviously we're plugging this in at 0, 1. And I'm just writing this right here just to indicate that, but we're good. 3 minus 1 cosine of 0. 3 minus 1 is 2 cosine of 0. If we look at a unit circle, that's right there. 1, 0. Cosine is the x value. 1, so we get 2. So this is 2x minus 0. All right, there is my equation for the line tangent. Then it says use the equation to approximate f of 0.2. Cool. Y minus 1 is equal to 2. 0.2 minus 0. So y minus 1 is equal to 2 times 0.2. So y minus 1 is equal to 2 times 2 is 4, but because of the point, it's 0.4. Add 1. Bam, y is equal to 1.4. Now we can write f of 0.2 or 0.2 is approximately, because it said approximate, 1.4. And we're in business, we're golden, we're ready to move on, right? Those ones here, you know, didn't take long. Problems I think we can do. But the real money question comes up in part number 6. We got the function. It says y equals f of x. Find y equals f of x. That's your key. You want the original. That's all that matters. We're looking for the OG when f of 0 equals 1. In other words, this is your x value. This is your y value. All right, let us begin. We need to find the original. We're given what? We are given the derivative. 3 minus y cosine of x. Bam. Cool, let's go ahead and separate the variables. So I'm going to multiply dx to both sides. And I'm going to divide by 3 minus y to both sides. And we're going to divide by 3 minus y to both sides. Okay, that cancels. I'm going to get 1 over 3 minus y. dy is equal to cosine of x dx. There it is. Okay, now that our variables have been separated, we're going to take the antiderivative. Bam. There's no power. This becomes ln absolute value of 3 minus y. But be careful. What's the derivative of the inside? This is -1, which since we're doing the anti, we divide by the -1. The other problem, we didn't have to worry about that because it was 1. In this case, it's -1. We do need to worry about that. Antiderivative of cosine is sine. X plus c. Let me double verify. Derivative of sine is cosine. Bam, we're good. Okay, we're good. All right, let me go ahead and rewrite this as, don't usually like to have a negative on the bottom, right? It's just negative. Again, as we went over, 2 divided by -1 is -2, right? 3 divided by -1 is -3. So let me just write this as negative ln absolute value of 3 minus y is equal to sine of x plus c. Let's plug in our points to find the c value. This is 3 minus 1 is equal to sine of 0 plus c. Sine of 0, unit circle, it's 1 comma 0. Sine is the y value, that's 0, gone. This is negative ln, and then this is 2. Absolute value of 2 is 2, so we get that. Very good. All right, now let's go ahead and plug it back into my function, right? So we went from here to here. So now that we got our c value, let's plug it back in and solve. We get negative ln absolute value of 3 minus y is equal to sine of x minus ln of 2. What I want to do first, before I do e to both sides, is you got to get rid of the negative symbol. So I'm going to multiply negative across a -1, I guess you want to call it, across to everything, right? Negative times negative. Let me just scroll down. Negative times negative is a positive. We get ln absolute value of 3 minus y. Negative times sine is negative sine x. Negative times negative ln is positive ln of 2. Now what do we do to get rid of ln? Well, we raise e to both sides. 3 minus y is equal to e to the negative sine of x plus ln of 2. Okay, now let's subtract 3 to both sides. Boom. So let's subtract 3 to both sides. And we're just kind of solving this out, right? And I'm kind of going through kind of quickly, but hopefully this makes sense. Negative y is equal to e to the negative sine of x plus ln of 2 minus 3. Now to get rid of the negative, we multiply -1 to both sides. -1, we get y is equal to, again, the power on e stays the same. That will never change, right? So it's going to be -1 times the e to blah, blah, blah is negative e to blah, 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 which is a negative sine of x plus ln of 2. Negative times a negative with the -3 becomes a positive 3. Bam, there it is. We got our function. We are in business. We're good to go, right? So that kind of takes care of the problem for us there. And like I said, it's we're doing pretty darn good. So with that being said, let's see how long that took me, which is about 8 minutes, right? So I went through this probably faster than you should, but hopefully this all kind of made sense as we kind of went through. I felt like it was a very fair problem, and I think what was maybe the biggest thing was keeping in mind that you had when you took the antiderivative of 1 over 3 minus y, it was ln, but we had to divide by that -1, right? No different than if we had, let's say, 1 over 2 minus 4y. The antiderivative of this would be ln absolute value of 2 minus 4y. Derivative of the inside is -4, so we divide by -4, right? Now, how would that change our problem? That just means that the negative moves up front. So let's just change this as -1 over 4 ln absolute value of 2 minus 4y, right? You could leave it like that instead, right? Which could complicate things, but nonetheless, the principle is still the same. All right, take care.